Hello, everyone. In this video, we're going to look at example 1 in section 4.3. This is where it's going to get pretty exciting because we're actually going to compute the equation of a tangent line. And what I hope you'll see is that a lot of the work that we do is going to look very familiar to what you've seen in a differential calculus class. We're just putting it together in a new way to work with a multivariable function. All right, so let's go ahead and get started here. So in example 1, we're told to let f of x be the function y plus 1 times e to the x squared plus y squared. And we're going to find the tangent plane to f at the point 0, 0. So first of all, just take a deep breath. This function does look a little complicated, right? Because we have a product, we have e, that always makes things scary. But we're just going to be kind of untangling it slowly. And you'll see that a lot of the pieces for finding the equation of a tangent plane really just fall out. Okay, so first of all, let's just recall what the equation of a tangent plane is. So going back to our work from the previous section, we saw the equation of the tangent line here, but filling in what m and n are, just those partials with respect to x and y, we get this equation here. So this equation in the box is also, it's an approximation for our function, but it is the equation of the tangent plane. I'm just going to write that out to really bring that home. So this is the equation of the tangent plane of f at the point AB. Okay, so we just need to write out that equation for us in our example. And so typically we make this z equals. So the output equals this equation or this expression. All right, so what do we need to compute then? Well, we need f of AB, we need f sub x of AB, and we need f sub y of AB. And after those three things, we're going to be set with our equation. So let's go ahead and compute that. Why don't we start with computing those partial derivatives? All right, so we're going to compute the partial derivative with respect to x. In other words, df dx. So what does it look like to compute a partial derivative of f? So essentially, if we look at the function y plus 1 times e to the x squared plus y squared, what we want to do is compute the derivative of this function with respect to x. Meaning, whenever we see y or an expression like y like this, we're going to treat it like just a constant. So this becomes equal to then y plus 1, the constant just comes out, times the derivative of e to the x squared plus y squared with respect to x. So here we see that x is involved in the exponent of e, and so we need to take a chain rule to first take the derivative of the outside and then multiply by the derivative of the inside. So that would just look like we'd have y plus 1 still. So it would look like e to the x squared plus y squared. Again, that's just the derivative of e to the whatever is equal to e to the whatever. So we just leave that there. And then we multiply by the derivative of x squared plus y squared with respect to x. So again, y and y squared is just a constant. So this would just look like y plus 1 times e to the x squared plus y squared times 2x. Because that y squared, just a constant, would go away. Okay, not bad, huh? So we just computed the partial derivative of f with respect to x. Okay, so now let's do that with the partial derivative of f with respect to y. So here we're looking at y plus 1 times e to the x squared plus y squared, and we want to take the derivative of that with respect to y. So now we're treating x like a constant, but y is now our changing variable. So notice we have a product here. So we're multiplying together two terms that contain the y. So we need to use the product rule. I'll just write that down to emphasize that. So first we can take the derivative of the first. So I'm going to go ahead and write this out just so you see all the details. Derivative of y plus 1 with respect to y times the second, e to the x squared plus y squared, plus the first, y plus 1, times the derivative of the second. All right, and just to clean things up, I'm just going to circle this so we know that it is separate from the work that we're doing. This is f sub x. All right, so now we can just compute those derivatives. So derivative of y plus 1 is just 1. So this becomes 1 times e to the x squared plus y squared. Then we have y plus 1. And so the derivative here of e to the x squared plus y squared is, again, using the chain rule. That just becomes the derivative of e to the whatever, is just e to that whatever, e to the x squared plus y squared, times the derivative of that exponent. X is a constant here, so we just have 2y. So then this is our partial with respect to y. And we can clean this up here. I don't need this 1 because we're just multiplying by 1, no big deal. So this would be our partial with respect to y. And we could simplify this further. I'm not too worried about that. What I am worried about, though, is about taking that derivative, keeping the value or the variable that we're not varying constant. Okay, cool. So we have those partials, so we're getting close. So what we want to do now is compute the partials with respect to x and y, but at the point 0, 0. So first we're going to use our f sub x of xy and just plug in 0 for x and 0 for y. So that looks like 0 plus 1 times e to the 0 squared plus 0 squared times 2 times 0. Well, that all falls out to be 0. And then f sub y of 0, 0, we're going to use this partial here. So I'm going to plug in 0, 0, or 0 for x and 0 for y. So we get e to the 0 squared plus 0 squared plus 0 plus 1 times e to the 0 squared plus 0 squared times 2 times 0. So e to the 0 is just 1. And we get plus 1 times e to the 0 times 2 times 0. We're multiplying, but we have a 0 in there, so we just get 0. So in the end, we get 1. So now the final component that we need, looking back at our equation here, we found these f sub x of 0, 0 and f sub x of y of 0, 0. We just need f of ab. So again, our AB is 0, 0. So we just need f evaluated at 0, 0. So we just look at our function here, plug in 0 for x and 0 for y. So there we get 0 plus 1 times e to the 0 squared plus 0 squared. So we get 1 times e to the 0, just 1. So we get 1. All right, so now we have that final component. All right, so let's put all these pieces together. So feel free to get out a new page to start writing on. I'm just going to continue writing down here, and then I'll clean it up for the next video. All right, so in writing our tangent plane, we just need to put these pieces together. So we're going to have z equals f of 0, 0. I'm going to write it out and just fill in the components. Times f sub x of 0, 0 times x minus 0 plus f sub y of 0, 0 times y minus 0. So notice I'm just filling in those components for the equation of the tangent plane. All right, so now let's gather what we just computed. So we have f of 0, 0 is 1. We have f sub x of 0, 0 is 0. And we have f sub y of 0, 0 is 1. So we can fill in those values here. So this just becomes 1 plus 0 times x minus 0 plus 1 times y minus 0, which if we simplify becomes 1 plus y. So the equation of our tangent plane looks like z equals 1 plus y. So notice we no longer have an x variable here. So what that means is that the tangent plane is the same regardless of what x you're using. So it means that it's going to be, which will mean essentially wherever you are in the x value, as you vary the x, the output is going to stay the same. And you can kind of maybe think about what that image should look like. All right, so now let's take a look at part B. And first I'm going to clean up my work a little bit here so we have some room to play with. So in part B, we're asked to use the tangent plane to approximate f of 0.1 rather, 0.1, and compare your answer with the exact value of f. So let's go ahead and start with computing that exact value of f at 0.1, 0.1. So recall our function looks like f of xy equals y plus 1 times e to the x squared plus y squared. So the exact value would be f of 0.1, 0.1 would equal 0.1 plus 1 times e to the 0.1 squared plus 0.1 squared. So I'm going to have to get out my calculator to do that, so I encourage you to follow along. And I get something close to 1.1222 repeating with that 2 repeats. So this is what we'd say is the exact value of f of 0.1, 0.1. Okay, so now let's consider how to approximate that value using the tangent plane. So what that means is rather than use this function itself, what we can do is use that tangent plane that we found in part A. So here I've rewritten it for our convenience because I cleaned it up before. So that tangent plane was z, the output is equal to 1 plus y. So for the approximation, we can use that tangent plane instead to approximate that value. So f of 0.1, 0.1 is going to be about equal to the value of 1 plus y, which is our tangent plane, evaluated at the point 0.1, 0.1. I'm just using some notation here. You've probably seen this when you're computing integrals or when you're looking at those partial derivatives. So now I'll plug in 0.1 for y. So we get 1 plus 0.1, which is just 1.1. So here is our approximate value of f of 0.1, 0.1. So a couple things to notice is first, this value, the approximation is fairly close to the exact value. So it does a pretty good job. But notice it won't always do a good job in that we need that input that we're evaluating at to be close to 0, 0, which is the point that we used to make that tangent plane, or rather is the point that we computed the tangent plane at. So we can see here that yes, indeed, this tangent plane does a pretty good job of approximating our function near the point 0, 0. Awesome, great work, everyone.